This mini lecture will cover the concept of centroid, moment of inertia, also known as rotational inertia, and the concept of the parallel axis theorem, a method by which you will analyze an object that is rotating around an axis that is not its centroid. In order to understand this mini lecture, students should review the section 4 notes in Newton's second law of free body diagram analysis that are on the D2L page for Dynamics 265, specifically pages 1 through 19. That will cover material from high school on Newton laws of motion, friction, both static and kinetic, the drawing of free body diagrams, how you analyze and draw the free body diagram of an object that is moving on an incline, and when you have multiple objects in a mechanical system, how you do systems of equations in the mechanical system. There's a list of exercises on page 20 and 21 of the section 4 notes that students should understand and master. And the new concepts that we have recently covered in the Dynamics 265 class, the concept of net moment or torque, Newton's second law of rotation, which is net moment around axis P equals moment of inertia around axis P times angular acceleration. And we've done a few examples in class which covered the concept of taking an object and rotating it around an axis which is its centroid. So review those examples on pages 22 to 32 of the section 4 notes. The concept of centroid is a very important concept in mechanical analysis, because center of mass, or centroid, is the point where the object balances. So it is the point where the object balances by gravity So if I were to take an object like this wheel and put my finger at the centroid of the object, it will balance on my finger. The centroid is also the axis about which a minimum possible kinetic energy is expended. This means that it is easiest to rotate an object around its center of mass. So if I take this wheel and put it on an axis which is through its centroid, when I rotate this object, by exerting a force that is off the axis of rotation and causing it to have a clockwise torque and a clockwise spin, this object offers the minimum amount possible of moment of inertia, the minimum amount possible resistance to rotation when I try to rotate the object around an axis that goes through its center of mass. Also, the centroid is the object's natural axis of rotation. Left to its own devices, this object, if it is thrown through the air, this wheel, as it is thrown through the air, will exhibit rotation and curvilinear motion as it moves. If it was thrown up, it will travel through the air and travel in a predictable parabolic arc for the center of mass, and it will rotate around the object's center of mass. The concept of moment of inertia is related to the general concept of inertia, which is a measurement of an object's resistance to a change in its rotation. Inertia in general is a measurement of an object's resistance to its change in any kind of motion, but specifically moment of inertia or rotational inertia is a measurement of an object's resistance specifically to a change in rotation. When we talk about linear inertia, if you do this by comparison, Newton's second law for translation which should be familiar, net force is mass times acceleration. In Newton's second law for translation, the way that you analyze this question is you do the sum of the forces, the sum of the force vectors on one side of the equation, and on the other side of the equation, you have what resulting motion the object exhibits. So A vector, that is the acceleration that results. This would be measured in meters per second squared. And what scales the equation is the object's inertia. In this case, the object's linear inertia. An object's linear inertia is a measurement of its resistance to a change in straight line or translational motion. And it turned out that that is equivalent to the object's mass. And so if you take a kilogram times a meter per second squared, that is where we get the force unit of newtons from. In translational motion, the linear inertia, the mass of the object, is a property of that object. But in Newton's second law for rotation, where we do net moment equals moment of inertia times angular acceleration, there's a big difference in the way that you do this analysis because you cannot calculate moment vector without reference to an axis about which it spins, which means that your moment of inertia is also calculated in reference to the axis about which it spins. Moment of inertia, or rotational inertia, is not a property of the rigid body. It is not a property of the object when it is exhibiting rotation. It is a combination of the mass distribution of that object and the location of the axis about which it spins. So this is your net moment, calculated exactly the same way as it is done in statics. That would be measured in Newton times meters. Alpha is the angular acceleration that results. The angular acceleration that results, and that'll be in radians per second squared. And if you do the unit analysis, you will find that in order to make this equation match up to Newton meter for units, the units of moment of inertia are actually kilograms times square meters. That means mass times distance squared is the fundamental equation behind moment of inertia of a point. So you need to know both the mass of the object, but also how it is distributed relative to the axis of rotation. So rotational inertia is a number, a measurement of an object's resistance to a change in rotation, but it is always measured with respect to an axis of rotation. Therefore, it is not a property of the object like mass. You have to know both the mass distribution of the object and the location of the axis about which the object spins. Now, for a uniform disk, the moment of inertia of an object around its centroid is given by half the mass of the object times its radius squared. Now, this is not a uniform disk. But if it was a mass distribution that was even throughout, and I tried to spin this object around its axis of rotation that is through its center of mass, right? That's the easiest axis about which this thing will rotate. The amount of moment of inertia in kilograms square meters would be simply 1/2 times the mass of this object times the radius of the object squared. You can see the derivation of this equation on page 29 and 30 of the section 4 notes of Newton's second law free body diagram analysis that is available on the D2L page in module number 4 for Dynamics 265. So if I exert a force which is off the axis of rotation, the centroid, and cause this wheel to spin, that is the easiest axis about which this object can rotate. But for a rolling wheel, so if I take the same object but cause it to rotate around an axis which is not its centroid. So I'm going to have an object that's rolling. So if I take this wheel and try to roll it, oops, if I take this wheel and try to roll it around an axis of rotation, that when you see the wheel rolling, you will notice a distinctly different motion. This object has only one point on the entire object while it is rolling that is at rest. And it is the point of contact of the object, point of contact of the wheel, in contact with the surface upon which it is spinning. So specifically for a rolling wheel, or rolling disc, when we look at the wheel in its interaction with the surface upon which it rolls, there's only one point on the wheel which is at rest. And we're going to call this point P. It is the single point about which the object spins. Instantaneously, if I look at, as the wheel rolls to the right, the center of mass of the wheel will have a velocity which is directed to the right. But the top of the wheel will exhibit an object which is, the top of the wheel will exhibit a velocity which is exactly twice that as the velocity of the center of mass. The reason being that that point is exactly twice as far away from the axis of rotation as is the center of mass. An analogy that you can see is if I took a stick and had it pinned on one end, and I cause a torque on this object so that it exhibits a rotation that is clockwise. As this object moves from an initial position to a final position, and undergoes a rotation, you'll notice that the instantaneous velocity of a point halfway along the length of the rod and the velocity of a point the full length along the rod, the ratio of those two velocities is going to be 2 to 1. The instantaneous velocity of any point that is on this rotating object has to be a circular path around the center of rotation. The new axis of rotation, if I have a pinned stick, would be at the bottom of the stick. So all points on this object exhibit circular motion and are centered on that axis of rotation. So the rolling wheel behaves in exactly the same way because that is the only point on the object which is at rest. So if I take a radius vector from point P and go to any location on the object, you'll notice that these points are instantaneously exhibiting rotational motion, in this case clockwise rotational motion, both of which are centered on this axis of rotation. So even though the wheel is moving to the right, as it is rolling, this point of contact is the instantaneous center of rotation. If I go to the leading edge of the wheel or the trailing edge of the wheel, you'll notice that if I take a radius vector to those locations, those distances are a little bit longer than the distance to the center, but shorter than the distance to the top of the wheel. So it turns out that that distance at that location is square root of 2 times the radius. So we'll end up with 1.41 v, square root of 2 times v, at a 90-degree angle to that radius vector. And here we'll have exactly the same thing, 1.41 v, square root of 2v at a 90-degree axis, at a 90-degree angle to the radius vector. All of these objects, all these points that are on the object, exhibit the same type of rotation. They exhibit a angular velocity omega, which in this case is clockwise, around axis P. So the question becomes, when I have an object that is spinning around an axis that is not its center of mass, but in fact a point that is different than its center of mass, how do we calculate how difficult it is to spin? And that brings us to the concept of the parallel axis theorem. This is the method by which, for any two-dimensional plane motion of a rigid body, if you want to calculate the moment of inertia of the object around its new axis of rotation P in reference to its moment of inertia around axis C, the equation is relatively straightforward. The moment of inertia around axis P has to start from a minimum moment of inertia, a minimum resistance to rotation, around its centroid, IC. But what we're doing is we're taking, as though we have, remember, for a point mass, if I try to take a point mass and rotate that point mass around an axis of rotation, the distance from the axis of rotation is d. For a point mass, the moment of inertia, its resistance will be mass times distance squared. That should be a concept familiar to you from calculus, Math 288. So when I try to take a rolling wheel and roll it about an axis P, I'm in effect taking the entire mass, which is concentrated at its centroid, and trying to rotate that mass now around the axis P. So I'm going to have an additional resistance to the rotation of mass times the distance between the two axes, dpc, which is this distance right here, but squared, because moment of inertia goes as the square of the distance. So to calculate the moment of inertia of this wheel about an axis that is not its centroid, I have to take the minimum rotational inertia, the minimum moment of inertia, and add how much resistance would be offered if I tried to take the whole object and rotate it around that new axis of rotation. So you have to measure the distance from the new axis of rotation, point P, to the centroid, its minimum axis of rotation. It's a minimum moment of inertia axis of rotation. And so you add the mass times distance from P to C squared. You take this number, IP, and that's what goes into Newton's second law for rotation. In order for you to calculate this number, IP, you need to know both the moment of inertia of the object around its centroid and the distance from the object's center of mass to the new axis of rotation. If you have a uniform wheel, IC is known by this equation here. If it is a non-uniform wheel, you will have to be told what that number is, or you'll have to calculate it by some other means. Enter this equation into Newton's second law for rotation and analyze the free body diagram in that manner. That is the parallel axis theorem.